Sorry, I was just thinking about a pop can. Well, let's extend that a little further. Have you ever really thought about the number of reactions that go on around you in a room at any given time? Well, let's try and scale that down a bit and take that pop can I was thinking about and bring it into play. Now, inside a pop can, if we just think about the number of particles and collisions that are inside a pop can, the magnitude is really kind of hard to think about. Inside a pop can, there are 10 to the power of 30 molecular collisions every second. Every second. 10 to the 30. That's a value that's significantly larger than even a mole. And if we think about the major components of air, we're talking about nitrogen and oxygen. And nitrogen and oxygen, if they collide together under certain conditions, can form nitrogen dioxide, which is a kind of deadly toxic gas that we typically associate with photochemical smog. If all of those collisions that were happening per second, remember that 10 to the 30 collisions that were happening per second, if every single one of those was to result in a chemical reaction, well, all of those things would happen in about 5 times 10 to the negative 9 seconds, and we'd have an awful lot of poisonous toxic gas. Clearly, that doesn't happen. So there has to be something that comes into play here. And of course there is. Now, we're going to take a look at those factors, but first we have to understand the nature of reactions. In order for there to be a reaction, things have to collide. That is, reactions need particle collisions. Things have to collide in order to react. Now, there are a couple of things that must happen first. One, there has to be the proper orientation, or what we call collision geometry. Molecules, even if they collide together at high speeds, won't necessarily form a reaction or create a reaction unless they're oriented in the correct way. That is, there has to be an appropriate geometry. They have to hit in just the right way in order for there to be a reaction. But what we're going to focus on is the appropriate amount of energy. Particles need enough energy when they collide to create a reaction. And we call this activation energy. Now, activation energy is just the minimum amount of energy that's required for a particular reaction. If we understand that a collision results in a reaction, if we can increase the number of collisions, then we can increase the rate of the reaction. That is, if we can increase the number of collisions, we're increasing the likelihood that these collisions are going to be with the appropriate geometry and the appropriate amount of energy. So therefore, we're going to get more reactions and we're going to increase the rate. Now, it's important to note that sometimes we also want to decrease the rate of the reaction, so we can control and manipulate the number of collisions that way by decreasing the number of collisions and decreasing the likelihood that they're going to lead to an effective reaction. But let's just take a look at a scenario where we would want to increase the rate of the reaction. So by increasing the number of collisions, we could therefore increase the rate. Now, there's a couple things that we can do in order to enact this change or bring about this change in rate. The first thing is to think about the physical state. Now, in previous science courses, you might have referred to this as surface area, and really this just means we're trying to maximize the contact of one substance for another. Really, things just have to come in contact to react. So if we can maximize the surface area or space available for these particles to come in contact with each other, then we can increase the likelihood that these collisions are going to result in an effective reaction. If we think about temperature, and temperature is typically the one that people tend to associate most with speeding up or slowing down a reaction, well, if we can increase the motion of those particles, then we can increase the likelihood that they are going to result in a collision, and a collision with appropriate geometry, with appropriate energy, and ultimately result in a reaction. And finally, we can deal with concentration, which is really just determining the number of particles per unit volume or per unit area. And the more particles that we have in a particular area, the more likelihood that there is going to be a collision, the increased likelihood that there's going to be an effective collision, and therefore the increased likelihood that there's going to be a reaction. So all of these factors come into play when we're trying to manipulate a chemical reaction. So here we are in a crowd of people. I'm going to try and pretend that I'm a particle. And what I want to do is enact a response in the other particles around me. If I wanted to make sure that I randomly collided with one of these individuals with enough force to knock one of them over, 1, I would blindfold myself. 2, if I want to make sure I collide with somebody, it's probably best to do it in a really crowded area like this one. And 3, I'm probably going to want to move as fast as I possibly can, because if I just amble around and just bump into people, I'm probably not going to knock them over. Now, none of this is very nice, But if we think about this being analogous to a particle, we are trying to collide with enough energy to enact a response in another particle. So if we think about it this way, if we increase the number of people that are around us, we've increased the concentration of other particles in the area. If I blindfold myself, I'm doing so randomly, and if I move as fast as I possibly can, I'm increasing my kinetic energy and also increasing the likelihood that I'm going to collide with somebody with the appropriate amount of energy to enact a response, knocking them over. And I think if I knock these people over, I'd get a pretty good response out of them. So all of these things are analogous to some of the factors that we would control in a chemical reaction to increase the rate of our reaction. But what about surface area? Well, I'm kind of hungry. Let's see if I can find somewhere for lunch. Okay, well, here I am at a steakhouse. Now, at a steakhouse, I have a couple of options here. I could order a steak, or I could order a burger. Now, a steak really is just a slab of meat, and the surface area on a steak is just anything that you can really see, the top and the outer sides of that steak. The burger is made up of ground beef, which, for lack of a better explanation, is just a really, really long tube of compressed meat. Yeah. Anyway, if we think about cooking these two things, I could order my steak medium, well done, rare, medium rare. I'm a medium rare kind of guy, but the reason that I can order my steak like that and I cannot order my burger medium rare or rare is because of the bacteria coming in contact with the surface. With the steak, you can sear it on the top and bottom and cook it around the sides and leave the inside relatively untouched because the bacteria doesn't come in contact with the inside of the meat. However, the burger, which is, as I said, is just a really, really, really long tube of compressed meat, there's a lot more surface area, all that entire tube of ground beef that this bacteria could potentially come in contact with, and you want to make sure that it's thoroughly cooked because all that bacteria can reach the inside of the burger. So hopefully these analogies helped you understand the factors that we use to help us control the overall rate of a reaction. Now, which am I going to choose? Well, despite the long tube of compressed meat, I'm going to go with the burger because I'm cheap. Thanks for watching, and I'm going to dig in. Yummy pretend burger.